Mercury is the smallest planet in the solar system and the closest to the Sun. Its orbit around the Sun takes 87.97 Earth days, the shortest of all the Sun's planets. It is named after the Roman god Mercurius, Mercury, god of commerce, messenger of the gods, and mediator between gods and mortals, corresponding to the Greek god Hermes. Like Venus, Mercury orbits the Sun within Earth's orbit as an inferior planet, and its apparent distance from the Sun as viewed from Earth never exceeds 28 degrees. This proximity to the Sun means the planet can only be seen near the western horizon after sunset or the eastern horizon before sunrise, usually in twilight. At this time, it may appear as a bright star-like object but is often far more difficult to observe than Venus. From Earth, the planet telescopically displays the complete range of phases, similar to Venus and the Moon, which recurs over its synodic period of approximately 116 days. Mercury rotates in a way that is unique in the solar system. It is tidally locked with the Sun in a 3-to-2 spin-orbit resonance, meaning that relative to the fixed stars, it rotates on its axis exactly 3 times for every 2 revolutions it makes around the Sun. In a frame of reference that rotates with the orbital motion, it appears to rotate only once every 2 Mercurian years. An observer on Mercury would therefore see only 1 day every 2 Mercurian years. Mercury's axis has the smallest tilt of any of the solar system's planets, about 1/30th degree. Its orbital eccentricity is the largest of all that known planets in the solar system. At perihelion, Mercury's distance from the Sun is only about 2/3, or 66%, of its distance at aphelion. Mercury's surface appears heavily cratered and is similar in appearance to the Moon's, indicating that it has been geologically inactive for billions of years. Having almost no atmosphere to retain heat, it has surface temperatures that vary diurnally more than on any other planet in the solar system, ranging from 100 K, -173 degrees Celsius, -280 degrees Fahrenheit, at night to 700 K, 427 degrees Celsius, 800 degrees Fahrenheit, during the day across the equatorial regions. The polar regions are constantly below 180 K, -93 degrees Celsius, -136 degrees Fahrenheit. The planet has no known natural satellites. 2 spacecraft have visited Mercury. Mariner 10 flew by in 1974 and 1975. And Messenger, launched in 2004, orbited Mercury over 4,000 times in 4 years before exhausting its fuel and crashing into the planet's surface on April 30, 2015. The BP Colombo spacecraft is planned to arrive at Mercury in 2025. Name and symbol. The ancients knew Mercury by different names depending on whether it was an evening star or a morning star. By about 350 BC, the ancient Greeks had realized the 2 stars were one. They knew the planet as Stilben, meaning twinkling, and Hermes, for its fleeting motion, a name that is retained in modern Greek Hermes. The Romans named the planet after the swift-footed Roman messenger god, Mercury, translated in Latin as Mercurius, which they equated with the Greek Hermes, because it moves across the sky faster than any other planet. The astronomical symbol for Mercury is a stylized version of Hermes Caduceus. Physical characteristics. Mercury is one of 4 terrestrial planets in the solar system, and is a rocky body like Earth. It is the smallest planet in the solar system, with an equatorial radius of 2,439.7 kilometers, 1,516.0 miles. Mercury is also smaller, albeit more massive, than the largest natural satellites in the solar system, Ganymede and Titan. Mercury consists of approximately 70% metallic and 30% silicate material. Mercury appears to have a solid silicate crust and mantle overlying a solid, iron sulfide outer core layer, a deeper liquid core layer, and a solid inner core. The planet's density is the second highest in the solar system at 5.427 cubic centimeters, only slightly less than Earth's density of 5.515 cubic centimeters. If the effect of gravitational compression were to be factored out from both planets, the materials of which Mercury is made would be denser than those of Earth, with an uncompressed density of 5.3 cubic centimeters versus Earth's 4.4 cubic centimeters. Mercury's density can be used to infer details of its inner structure. Although Earth's higher density results appreciably from gravitational compression, particularly at the core, Mercury is much smaller and its inner regions are not as compressed. Therefore, for it to have such a high density, its core must be large and rich in iron. Geologists estimate that Mercury's core occupies about 55% of its volume. For Earth, this proportion is 17%. Research published in 2007 suggests that Mercury has a molten core. Surrounding the core is a 500 to 700 kilometers, 310 to 430 miles, mantle consisting of silicates. Based on data from the Mariner 10 mission and Earth-based observation, Mercury's crust is estimated to be 35 kilometers, 22 miles, thick. However, this model may be an overestimate and the crust could be 26 plus minus 11 kilometers, 16.2 plus minus 6.8 miles, thick based on an area isostasy model. One distinctive feature of Mercury's surface is the presence of numerous narrow ridges, extending up to several hundred kilometers in length. It is thought that these were formed as Mercury's core and mantle cooled and contracted at a time when the crust had already solidified. Surface geology. Mercury's surface is similar in appearance to that of the Moon, showing extensive mare-like plains and heavy cratering, indicating that it has been geologically inactive for billions of years. It is more heterogeneous than either Mars's or the Moon's, both of which contain significant stretches of similar geology, such as maria and plateaus. Albedo features are areas of markedly different reflectivity, which include impact craters, the resulting ejecta, and ray systems. Larger albedo features correspond to higher reflectivity planes. Mercury has dorsa, also called Drinkel ridges, moon-like highlands, mountains, plains, escarpments, and valleys. The planet's mantle is chemically heterogeneous, suggesting the planet went through a magma ocean phase early in its history. Crystallization of minerals and convective overturn resulted in layered, chemically heterogeneous crust with large-scale variations in chemical composition observed on the surface. The crust is low in iron but high in sulfur, resulting from the stronger early chemically reducing conditions than is found in the other terrestrial planets. The surface is dominated by iron-poor pyroxene and olivine, as represented by enstatite and phosphatite, respectively, along with sodium-rich plagioclase and minerals of mixed magnesium, calcium, and iron sulfide. The less reflective regions of the crust are high in carbon, most likely in the form of graphite. Names for features on Mercury come from a variety of sources. Names coming from people are limited to the deceased. Craters are named for artists, musicians, painters, and authors who have made outstanding or fundamental contributions to their field. Ridges, or dorsa, are named for scientists who have contributed to the study of Mercury. Depressions or fossae are named for works of architecture. Montes are named for the word hot in a variety of languages. Plains or planitia are named for Mercury in various languages. Escarpments or roops are named for ships of scientific expeditions. Valleys or vales are named for abandoned cities, towns, or settlements of antiquity, impact basins and craters. Mercury was heavily bombarded by comets and asteroids during and shortly following its formation 4.6 billion years ago, as well as during a possibly separate subsequent episode called the Late Heavy Bombardment that ended 3.8 billion years ago. Mercury received impacts over its entire surface during this period of intense crater formation, facilitated by the lack of any atmosphere to slow impactors down. During this time Mercury was volcanically active, basins were filled by magma, producing smooth plains similar to the Maria found on the Moon. An unusual crater with radiating troughs has been discovered that scientists called the Spider. It was later named Apollodorus. Craters on Mercury range in diameter from small bowl-shaped cavities to multi-ringed impact basins hundreds of kilometers across. They appear in all states of degradation, from relatively fresh rayed craters to highly degraded crater remnants. Mercurian craters differ subtly from lunar craters in that the area blanketed by their ejecta is much smaller, a consequence of Mercury's stronger surface gravity. According to International Astronomical Union, or IAU, rules, each new crater must be named after an artist who was famous for more than 50 years, and dead for more than 3 years, before the date the crater is named. The largest known crater is Caloris Planitia, or Caloris Basin, with a diameter of 1,550 kilometers. The impact that created the Caloris Basin was so powerful that it caused lava eruptions and left a concentric mountainous ring 2 kilometers tall surrounding the impact crater. The floor of the Caloris Basin is filled by a geologically distinct flat plain, broken up by ridges and fractures in a roughly polygonal pattern. It is not clear whether they are volcanic lava flows induced by the impact or a large sheet of impact melt. At the antipode of the Caloris Basin is a large region of unusual, hilly terrain known as the Weird Terrain. One hypothesis for its origin is that shock waves generated during the Caloris impact traveled around Mercury, converging at the basin's antipode, 180 degrees away. The resulting high stresses fractured the surface. Alternatively, it has been suggested that this terrain formed as a result of the convergence of ejecta at this basin's antipode. Overall, 46 impact basins have been identified. A notable basin is the 400 kilometers wide, multi-ring Tolstoj basin that has an ejecta blanket extending up to 500 kilometers from its rim and a floor that has been filled by smooth plains materials. Beethoven Basin has a similar-sized ejecta blanket and a 625 kilometers diameter rim. Like the Moon, the surface of Mercury has likely incurred the effects of space weathering processes, including solar wind and micrometeorite impacts, plains. There are 2 geologically distinct plains regions on Mercury. Gently rolling, hilly plains in the regions between craters are Mercury's oldest visible surfaces, predating the heavily cratered terrain. These intercrater plains appear to have obliterated many earlier craters, and show a general paucity of smaller craters below about 30 kilometers in diameter. Smooth plains are widespread flat areas that fill depressions of various sizes and bear a strong resemblance to the lunar Maria. Unlike lunar Maria, the smooth plains of Mercury have the same albedo as the older intercrater plains. Despite a lack of unequivocally volcanic characteristics, the localization and rounded, lobate shape of these plains strongly support volcanic origins. All the smooth plains of Mercury formed significantly later than the Caloris Basin, as evidenced by appreciably smaller crater densities than on the Caloris ejecta blanket. Compressional features. One unusual feature of Mercury's surface is the numerous compression folds, or roops, that crisscross the plains. As Mercury's interior cooled, it contracted and its surface began to deform, creating wrinkle ridges and lobate scarps associated with thrust faults. The scarps can reach lengths of 1,000 kilometers and heights of 3 kilometers. These compressional features can be seen on top of other features, such as craters and smooth plains, indicating they are more recent. Mapping of the features has suggested a total shrinkage of Mercury's radius in the range of 1 to 7 kilometers. Most activity along the major thrust systems probably ended about 3.6 to 3.7 billion years ago. Small-scale thrust fault scarps have been found, tens of meters in height and with lengths in the range of a few km, that appear to be less than 50 million years old, indicating that compression of the interior and consequent surface geological activity continued to the present. The Lunar Reconnaissance Orbiter discovered that similar but smaller thrust faults exist on the Moon. Volcanism. Picasso Crater, The large arc-shaped pit located on the eastern side of its floor are postulated to have formed when subsurface magma subsided or drained, causing the surface to collapse into the resulting void. There is evidence for pyroclastic flows on Mercury from low-profile shield volcanoes. 51 pyroclastic deposits have been identified, where 90% of them are found within impact craters. A study of the degradation state of the impact craters that host pyroclastic deposits suggests that pyroclastic activity occurred on Mercury over a prolonged interval. A rimless depression inside the southwest rim of the Caloris Basin consists of at least 9 overlapping volcanic vents, each individually up to 8 kilometers in diameter. It is thus a compound volcano. The vent floors are at least 1 kilometer below their brinks, and they bear a closer resemblance to volcanic craters sculpted by explosive eruptions or modified by collapse into void spaces created by magma withdrawal back down into a conduit. Scientists could not quantify the age of the volcanic complex system but reported that it could be of the order of 1 billion years. Surface conditions and exosphere. The surface temperature of Mercury ranges from 100 to 700 K, minus 173 to 427 degrees Celsius, minus 280 to 800 degrees Fahrenheit at the most extreme places. It never rises above 180 K at the poles, due to the absence of an atmosphere and a steep temperature gradient between the equator and the poles. The subsolar point reaches about 700 K during perihelion, but only 550 K at aphelion. On the dark side of the planet, temperatures average 110 K. The intensity of sunlight on Mercury's surface ranges between 4.59 and 10.61 times the solar constant. Although the daylight temperature at the surface of Mercury is generally extremely high, observations strongly suggest that ice exists on Mercury. The floors of deep craters at the poles are never exposed to direct sunlight, and temperatures that remain below 102 K, far lower than the global average. This creates a cold trap where ice can accumulate. Water ice strongly reflects radar, and observations by the 70-meter Goldstone Solar System radar and the VLA in the early 1990s revealed that there are patches of high radar reflection near the poles. Although ice was not the only possible cause of these reflective regions, astronomers think it was the most likely. The icy regions are estimated to contain about 1,014 to 1,015 kilograms of ice, and may be covered by a layer of regolith that inhibits sublimation. By comparison, the Antarctic ice sheet on Earth has a mass of about 4 times 1,018 kilograms, and Mars's south polar cap contains about 1,016 kilograms of water. The origin of the ice on Mercury is not yet known, but the two most likely sources are from outgassing of water from the planet's interior or deposition by impacts of comets. Mercury is too small and hot for its gravity to retain any significant atmosphere over long periods of time. It does have a tenuous surface-bounded exosphere containing hydrogen, helium, oxygen, sodium, calcium, potassium and others at a surface pressure of less than approximately 0.5 nPa, 0.005 picobars. This exosphere is not stable. Atoms are continuously lost and replenished from a variety of sources. Hydrogen atoms and helium atoms probably come from the solar wind, diffusing into Mercury's magnetosphere before later escaping back into space. Radioactive decay of elements within Mercury's crust is another source of helium, as well as sodium and potassium. MESSENGER found high proportions of calcium, helium, hydroxide, magnesium, oxygen, potassium, silicon and sodium. Water vapor is present, released by a combination of processes such as comets striking its surface, sputtering creating water out of hydrogen from the solar wind and oxygen from rock, and sublimation from reservoirs of water ice in the permanently shadowed polar craters. The detection of high amounts of water-related ions like O+, O-, and H3O+ was a surprise. Because of the quantities of these ions that were detected in Mercury's space environment, Scientists surmise that these molecules were blasted from the surface or exosphere by the solar wind. Sodium, potassium and calcium were discovered in the atmosphere during the 1980 to 1990s, and are thought to result primarily from the vaporization of surface rock struck by micrometeorite impacts, including presently from Comet Inc. In 2008, magnesium was discovered by MESSENGER. Studies indicate that, at times, sodium emissions are localized at points that correspond to the planet's magnetic poles. This would indicate an interaction between the magnetosphere and the planet's surface. On November 29, 2012, NASA confirmed that images from MESSENGER had detected that craters at the North Pole contained water ice. MESSENGER's principal investigator Sean Solomon is quoted in the New York Times estimating the volume of the ice to be large enough to encase Washington, D.C. in a frozen block 2.5 miles deep, magnetic field and magnetosphere. Despite its small size and slow 59-day-long rotation, Mercury has a significant, and apparently global, magnetic field. According to measurements taken by Mariner 10, it is about 1.1% the strength of Earth's. The magnetic field strength at Mercury's equator is about 300 nt. Like that of Earth, Mercury's magnetic field is dipolar. Unlike Earth's, Mercury's poles are nearly aligned with the planet's spin axis. Measurements from both the Mariner 10 and MESSENGER space probes have indicated that the strength and shape of the magnetic field are stable. It is likely that this magnetic field is generated by a dynamo effect, in a manner similar to the magnetic field of Earth. This dynamo effect would result from the circulation of the planet's iron-rich liquid core. Particularly strong tidal heating effects caused by the planet's high orbital eccentricity would serve to keep part of the core in the liquid state necessary for this dynamo effect. Mercury's magnetic field is strong enough to deflect the solar wind around the planet, creating a magnetosphere. The planet's magnetosphere, though small enough to fit within Earth, is strong enough to trap solar wind plasma. This contributes to the space weathering of the planet's surface. Observations taken by the Mariner 10 spacecraft detected this low-energy plasma in the magnetosphere of the planet's night side. Bursts of energetic particles in the planet's magnetotail indicate a dynamic quality to the planet's magnetosphere. During its second flyby of the planet on October 6, 2008, MESSENGER discovered that Mercury's magnetic field can be extremely leaky. The spacecraft encountered magnetic tornadoes, twisted bundles of magnetic fields connecting the planetary magnetic field to interplanetary space, that were up to 800 kilometers wide or a third of the radius of the planet. These twisted magnetic flux tubes, technically known as flux transfer events, form open windows in the planet's magnetic shield through which the solar wind may enter and directly impact Mercury's surface via magnetic reconnection. This also occurs in Earth's magnetic field. The MESSENGER observations showed the reconnection rate is 10 times higher at Mercury, but its proximity to the Sun only accounts for about a third of the reconnection rate observed by MESSENGER. Orbit, rotation, and longitude. Mercury has the most eccentric orbit of all the planets in the solar system. Its eccentricity is 0.21, with its distance from the Sun ranging from 46 million to 70 million kilometers, 29 million to 43 million miles. It takes 87.969 Earth days to complete an orbit. The diagram illustrates the effects of the eccentricity, showing Mercury's orbit overlaid with a circular orbit having the same semi-major axis. Mercury's higher velocity when it is near perihelion is clear from the greater distance it covers in each 5-day interval. In the diagram, the varying distance of Mercury to the Sun is represented by the size of the planet, which is inversely proportional to Mercury's distance from the Sun. This varying distance to the Sun leads to Mercury's surface being flexed by tidal bulges raised by the Sun that are about 17 times stronger than the Moon's on Earth. Combined with a 3-to-2 spin orbit resonance of the planet's rotation around its axis, it also results in complex variations of the surface temperature. The resonance makes a single solar day. The length between two meridian transits of the Sun, on Mercury last exactly 2 Mercury years, or about 176 Earth days. Mercury's orbit is inclined by 7 degrees to the plane of Earth's orbit, the ecliptic, the largest of all 8 known solar planets. As a result, transits of Mercury across the face of the Sun can only occur when the planet is crossing the plane of the ecliptic at the time it lies between Earth and the Sun, which is in May or November. This occurs about every 7 years on average. Ground-based telescopic research. The first telescopic observations of Mercury were made by Galileo in the early 17th century. Although he observed phases when he looked at Venus, his telescope was not powerful enough to see the phases of Mercury. In 1631, Pierre Gassendi made the first telescopic observations of the transit of a planet across the Sun when he saw a transit of Mercury predicted by Johannes Kepler. In 1639, Giovanni Zuppi used a telescope to discover that the planet had orbital phases similar to Venus and the Moon. The observation demonstrated conclusively that Mercury orbited round the Sun. A rare event in astronomy is the passage of one planet in front of another, occultation, as seen from Earth. Mercury and Venus occult each other every few centuries, and the event of May 28, 1737 is the only one historically observed, having been seen by John Beevers at the Royal Greenwich Observatory. The next occultation of Mercury by Venus will be on December 3, 2133. The difficulties inherent in observing a Mercury mean that it has been far less studied than the other planets. In 1800, Johann Schroter made observations of surface features, claiming to have observed 20-kilometer-high, 12-mile, mountains. Friedrich Bessel used Schroter's drawings to erroneously estimate the rotation period as 24 hours and an axial tilt of 70 degrees. In the 1880s, Giovanni Schiaparelli mapped the planet more accurately, and suggested that Mercury's rotational period was 88 days, the same as its orbital period due to tidal locking. This phenomenon is known as synchronous rotation. The effort to map the surface of Mercury was continued by Eugenio Antoniadi, who published a book in 1934 that included both maps and his own observations. Many of the planet's surface features, particularly the albedo features, take their names from Antoniadi's map. In June 1962, Soviet scientists at the Institute of Radio Engineering and Electronics of the USSR, Academy of Sciences, led by Vladimir Kotelnikov, became the first to bounce a radar signal off Mercury and receive it, starting radar observations of the planet. 3 years later, radar observations by Americans Gordon H. Pettengill and Rolf B. Dice, using the 300-meter Arecibo radio telescope in Puerto Rico, showed conclusively that the planet's rotational period was about 59 days. Research with space probes. Reaching Mercury from Earth poses significant technical challenges, because it orbits so much closer to the Sun than Earth. A Mercury-bound spacecraft launched from Earth must travel over 91 million kilometers, 57 million miles, into the Sun's gravitational potential whirl. Mercury has an orbital speed of 47.4 kilometers per second, 29.5 miles per second, whereas Earth's orbital speed is 29.8 kilometers per second, 18.5 miles per second. Therefore, the spacecraft must make a large change in velocity, delta V, to get to Mercury and then enter orbit, as compared to the delta V required for, say, Mars planetary missions. The potential energy liberated by moving down the Sun's potential whirl becomes kinetic energy, requiring a delta V change to do anything other than pass by Mercury. Some portion of this delta V budget can be provided from a gravity assist during one or more flybys of Venus. To land safely or enter a stable orbit, the spacecraft would rely entirely on rocket motors. Aerobraking is ruled out because Mercury has a negligible atmosphere. A trip to Mercury requires more rocket fuel than that required to escape the solar system completely. As a result, only 2 space probes have visited it so far. A proposed alternative approach would use a solar sail to attain a Mercury synchronous orbit around the Sun. Mariner 10. The first spacecraft to visit Mercury was NASA's Mariner 10, 1974 to 1975. The spacecraft used the gravity of Venus to adjust its orbital velocity so that it could approach Mercury, making it both the first spacecraft to use this gravitational slingshot effect and the first NASA mission to visit multiple planets. Mariner 10 provided the first close-up images of Mercury's surface, which immediately showed its heavily cratered nature, and revealed many other types of geological features, such as the giant scarps that were later ascribed to the effect of the planet shrinking slightly as its iron core cools. Unfortunately, the same face of the planet was lit at each of Mariner 10's close approaches. This made close observation of both sides of the planet impossible, and resulted in the mapping of less than 45% of the planet's surface. The spacecraft made 3 close approaches to Mercury, the closest of which took it to within 327 kilometers, 203 miles, of the surface. At the first close approach, instruments detected a magnetic field. To the great surprise of planetary geologists, Mercury's rotation was expected to be much too slow to generate a significant dynamo effect. The second close approach was primarily used for imaging, but at the third approach, extensive magnetic data were obtained. The data revealed that the planet's magnetic field is much like Earth's, which deflects the solar wind around the planet. For many years after the Mariner 10 encounters, the origin of Mercury's magnetic field remained the subject of several competing theories. On March 24, 1975, just 8 days after its final close approach, Mariner 10 ran out of fuel. Because its orbit could no longer be accurately controlled, mission controllers instructed the probe to shut down. Mariner 10 is thought to be still orbiting the Sun, passing close to Mercury every few months. Messenger. A second NASA mission to Mercury, named Messenger, Mercury Surface, Space Environment, Geochemistry, and Ranging, was launched on August 3, 2004. It made a flyby of Earth in August 2005, and of Venus in October 2006 and June 2007 to place it onto the correct trajectory to reach an orbit around Mercury. A first flyby of Mercury occurred on January 14, 2008, a second on October 6, 2008, and a third on September 29, 2009. Most of the hemisphere not imaged by Mariner 10 was mapped during these flybys. The probe successfully entered an elliptical orbit around the planet on March 18, 2011. The first orbital image of Mercury was obtained on March 29, 2011. The probe finished a 1-year mapping mission, and then entered a 1-year extended mission into 2013. In addition to continued observations and mapping of Mercury, Messenger observed the 2012 solar maximum. The mission was designed to clear up 6 key issues: Mercury's high density, its geological history, the nature of its magnetic field, the structure of its core, whether it has ice at its poles, and where its tenuous atmosphere comes from. To this end, the probe carried imaging devices that gathered much higher resolution images of much more of Mercury than Mariner 10, assorted spectrometers to determine abundances of elements in the crust, and magnetometers and devices to measure velocities of charged particles. Measurements of changes in the probe's orbital velocity were expected to be used to infer details of the planet's interior structure. Messenger's final maneuver was on April 24, 2015, and it crashed into Mercury's surface on April 30, 2015. The spacecraft's impact with Mercury occurred near 3:26 p.m. EDT on April 30, 2015, leaving a crater estimated to be 16 meters, 52 feet, in diameter. Bepi-Colombo. The European Space Agency and the Japanese Space Agency developed and launched a joint mission called Bepi-Colombo, which will orbit Mercury with 2 probes, one to map the planet and the other to study its magnetosphere. Launched on October 20, 2018, Bepi-Colombo is expected to reach Mercury in 2025. It will release a magnetometer probe into an elliptical orbit, then chemical rockets will fire to deposit the MAPA probe into a circular orbit. Both probes will operate for 1 terrestrial year. The MAPA probe carries an array of spectrometers similar to those on Messenger, and will study the planet at many different wavelengths including infrared, ultraviolet, X-ray and gamma ray. That concludes this week's video on the planet Mercury. It has been a pleasure to share the majesty of this barren planet, and I hope you have learned something new today. In the next video we will be covering the planet Venus. This is Infinite Universe, and if you found the video useful and enjoy our content, please give us a like and hit the subscribe button, as it reaches more people and helps this channel grow. It also allows us to make more content. You can watch the full hour version of this video when you join our Patreon. This will also gain you early access to future videos and additional content not released to YouTube. So until next time, stay safe and look to the stars.